give you a flavor of, is that loud enough? Okay. Of the various experimental activities that are currently taking place at the Department of Physics of the University of Cape Town, UCT. Right. I'm here with my colleagues and students from the Department of Physics. We are working on establishing the UCT CERN group, which is currently headed by Professor Jean Clemens, who is a phenomenologist on the search for the quark-gluon plasma. What I will do, since I assume that you've attended Professor Martin's lectures, Dr. Ellis's lectures, that I will just give you a quick snapshot of the theory of strong interactions, that is the theory of quantum chromodynamics. Look into a little bit of detail into what the QGP, quark-gluon plasma, is all about. Okay? I will talk mostly about the experimental techniques as an experimentalist. I'll give you an outline of the kind of tools and gadgets that we use to unpack nature at its most fundamental level. And please, I talk very fast with a strongly Zulu-accented English. Stop me if you understand anything. Okay? Right. So, our involvement from the experimental point of view is largely with the ALICE detector. I'll give you an outline of a spectrometer that we're actually looking at in close detail, the dimuon spectrometer. So the talk is largely experimental in its nature, just to give you an idea of various approaches that people have in trying to solve nature's most pressing problems. The Greek word, in Italian, a Greek word is called a polyethic. Take a diamond, it looks better if you look at it from different angles. Okay, so this is looking at the same problem from an experimental angle. I hope you appreciate that. Okay, we know that our current theory that describes strong interactions is zeroed in green here, can largely be understood in terms of fundamental constituents, right? You know, we've got quarks, gluons, and the mediating particles are gluons, and that has been covered and outlined in detail. Its residue is rather complicated. It results in the formation of nuclei and the interactions between protons and neutrons. Okay. A bit of detail about the strong force. Okay, nuclear physics is in this range. That's the pion that mediates the interaction between one nucleon and the other, Yukawa potential. If you now probe deeply, take this nucleon, expand it, home in, you realize that the nucleon, I don't want to bore you with that because you've covered this in detail already, is made up of 3 quarks, right? And these quarks interact by mediating gluons. Okay, here is a state of 3 quarks that have the same quantum number. They all have up, up, up. Right, what differs? What makes them not disobey the Pauli exclusion principle is what? I mean, you've got 3 up quarks here. According to the Pauli exclusion, they shouldn't be here, right? The reason why you obtain this fermionic state is because you have an antisymmetric wave function as a result of different color states. Okay, so quarks carry color. And these quarks form together into clusters of baryonic color singlets. And also, you can have a quark and antiquark pair, which are your mesons. John Ellis worked on this in the 1970s, where we know that you cannot even pull a proton apart. In nuclear physics, though, you can. There are models called the distorted wave impulse approximation. If I have high enough energy, say all of you are trapped in a potential here, right? And I come with a lot of energy, and I can pull Robert and plug him out. If Robert is a nucleon, okay, it's called scattering amplitude. You can scatter and extract one nucleon from the bulk of a nucleus. Although these nuclei interact strongly, but you can, in the nuclear realm, take one isolated neutron, which is why you can see a proton. However, you can't see a single quark. If there were 3 of you bound in a quark, bound in the potential of a proton, the quark potential, I would not have been able to kick this quark out or parton. Okay? I transfer energy in deep inelastic scattering, that's Q. If this is high enough, so as to change the flux line of this and distort it, I will not see a single quark, right? This quark will shower into a bunch of hadrons because of E equals mc squared. I put enough energy into the system, instead of being isolated, it will do what? It will hadronize. Likewise, yeah, if I take 2 quarks, put enough energy, you form a shower of hadrons. This is the famous string fragmentation model, which basically gave birth to the field of string theory, which you've which you've all been hearing about. Now, I will talk about the two regimes of quantum chromodynamics. Okay? There is a regime in which this QCD is perturbative. Therefore, we can calculate the cross-sections from first principle using the Feynman integral. All right, so just have a Lagrangian like you have for QCD, minimize and calculate the cross-section. And this only works if the transferred form momentum is very large. Okay? And this only works very well for high Q squared and short distances. However, in real nature, we hardly see any free quarks. So we are in the realm of non-perturbative QCD, which at the moment cannot be explained from first principles. So a lot of people have worked very hard in trying to understand this. So to conclude, on this very brief intro into QCD, one notes that you are dealing with a very complex but rich theory. Okay, I'm sure you've heard this already from the previous lectures. We know that these interactions depend on scale. You have non-perturbative QCD if you're in the long wavelength, short distance range. With a short wavelength, long wavelength, high energy. If you're in the short wavelength, high momentum transfer, high energy, you start somehow using some perturbative approximation to your theory of strong interactions. You also know that you don't have any free partons, because if you pull them out, you have hadronization. Also, we do not actually understand how QCD works in its proper theoretical context. So somehow we rely on models. Okay, and this is the biggest challenge facing theory and experiment, actually, how to understand this inner structure of strongly interacting matter. Now, since we are going to talk about the quark-gluon plasma, the quark-gluon plasma is nothing but a study of the analysis of change of phase from one form to the other. How? Let's look at the normal phases of matter. You have ice. If you add heat to ice, what happens to it? It melts, doesn't it? Q equals mc delta T, right? And if you add more heat into water, it warms up to 100 degrees centigrade, to 373. And what happens if you add more heat? You undergo a phase change from one form to the other. Okay? So this is a grade 12, standard 10 phase diagram that you all are familiar with. So now it's known that there is another phase of matter which is called a plasma. Now let's look at it in the context of QCD. Using the same analogy, it's just nothing but a simple phase transition. Of course, it's a bit more complicated than that, but nonetheless, you just need to understand everything in terms of movement from one phase to the other. Fundamental constituents are the same. Water molecules are the same. Just have changed from one solid to a liquid. Here's our proton, which in the context of nuclear physics is analyzed in a liquid form model. And if you take this atomic nucleus, this is where we are, 1 GeV per Fermi. If you increase the density, you go through another regime. Okay, this is a phase boundary, which is defined by some sort of a chemical freeze-out process. You go into a different regime of this quark-gluon plasma, which you don't understand yet. Okay, and another way of exploring this is, of course, by invoking a Big Bang, and a Big Bang only occurs once. However, modern accelerators, which lie here, depending on the energy, can somehow replicate this phase diagram, okay? By raising the temperature, for example, the SPS, which I'll talk about in a second, is in this range here. So by increasing the temperature, one can go into the quark-gluon plasma. Take a hadron, pump enough temperature into it, energy, it will melt. Okay? Or by increasing the density, one obtains this so-called new state of matter. Other questions? All I've just done is to introduce the notion of a change of phase from hadronic to the quark-gluon plasma. Now, where do we find this plasma? This plasma was obtained 15 billion years ago. About a millionth of a microsecond after the Big Bang, according to the standard model of cosmology, quarks and gluons were roaming about. All right? Then, of course, as something cools, when you cool something, what does it do? It coagulates, right? So these quarks and gluons coagulated into forming protons, and so on and so forth. In a lab, some theoreticians have attempted to model this in form of lattice QCD. So they take a three-dimensional grid and try to replicate how a proton works. And they've been able to calculate the transition temperatures. So for that, I'll not go into detail because it's a bit more complicated. And I'll try to focus myself on the experimental accelerators, because the title of my talk was originally on colliders. So colliders are the other avenues where one can obtain this quark gluon plasma. So you can study QCD matter at very high temperatures and densities. Another system in which one can obtain this QGP is at the center of neutron stars. Okay, let's look at how our heavy ions look like when you collide them. Okay, which is what you do. You collide these heavy ions. Because they are accelerated at ultra-relativistic energies, what's going to happen? Take something, you accelerate it, it's going to contract, isn't it? So you've got these two pancakes that are going to collide with each other. Okay? And they are Lorentz contracted because of in the rest frame, they are boosted with very high energies. They will collide, but there's a problem with the slide. Can someone tell me why? Okay, it's computer generated. Why is there a problem? The solution is at the bottom. Bruce? Okay. Just from your standard relativistic kinematics, these are ultra-relativistic. They're very close to the speed of light, right? Then you have this collision. You see these green balls here, these green pebbles. But why do we have this? Just from relativity. This is incorrect. Okay, Bruce?
Well, particles that have been knocked out must have interacted already. And since the nuclei haven't even seen each other yet, they can't have interacted and moving faster than the speed of light. So that's an effect of the code.
Okay, so there's a bug in the code. This is emulation. So, as Bruce said, these particles that are here saw each other long before the collision took place. So that means that they must have seen each other, they must have traveled faster than the speed of light, which makes them tachyons. Okay, so this is unrealistic. There's just a bug in the program. Okay, so...
You didn't write the code.
No, the code was written by these guys. All right. After collision, you have a lot of energy, E equals mc squared, right? So you convert all that energy into mass, so that's what you get. And then afterwards, this thing starts cooling down, so you can explain it in terms of some kind of it's like a thermal fireball that explodes. First, it's this huge collision, then you're almost replicating a Big Bang, then it explodes from the center, right? So you can understand some thermodynamics of the system that take place when the fireball is receding away from the collision point. Now, our aim is to understand QCD. Most importantly, the quark gluon plasma. And ask ourselves, does QCD become simpler at high temperature and high density? You need to understand the phase diagram of QCD, quantum chromodynamics. Also, as the evolution of computational power increases, we also need to understand lattice predictions, how well they agree with nature. How good are these computers in actually replicating the exact nature of strong interactions? You also need to understand the evolution after the collision of the nuclei. That's the experimental goal. And also we need to understand the early phase. When these particles start colliding, we need to find out what happened initially from studying the final phase. So these are the three ways of observing our quark gluon plasma. You look at the initial phase. What you see will be a huge number of particle multiplicities You look at the density of particles. You look at the collective behavior of this fireball that is hot. Find out if anything is hot, it will thermalize. A hot object cools down and thermalizes. So you need to find out its evolution of thermalization. Most interestingly, we need to understand this QGP, this quark-gluon plasma, in terms of hard probes. The most basic way of understanding it is by looking at the primordial state of matter right at when these quarks and gluons are roaming about. So you are really in the phase of looking at, sorry? Oh, is it? It's going to pick up, eh? Okay, now let's try to understand this in detail. This should be psi. It's a typo, sorry. I take two heavy colliding particles, work them together. What ought to have happened is a formation of this, one of the many particles we're looking at, is a so-called psi, which is a resonance of a charm and anti-charm pair. Okay, so, oh dear. This. Jeff, this might pick up, eh? The fan is. Or shall I just go at speed until it is hot? Okay, just switch off the. Okay, should we? Okay, here's an analogy. Robert and I always come in pairs. We are closely, we stick together. Under normal circumstances, we will remain as a pair. However, call this pair a psi. Okay, it's just a CC bar pair. One of the signatures of the quark-gluon plasma is when we enter a system. Now, Robert and I don't decouple away from each other. Okay, we stay coupled with Mr. Cook. What's your name? Mr. Cook, Martin. Okay, so therefore, if we are in this phase where we're just mingling with each other, that means you must have shielded the interaction of Robert and I from her. Okay, so that's one of the signatures of the quark-gluon plasma. The suppression of the formation of these strongly bound states. Okay, this is what is our focus at the moment. Psi suppression. The suppression or the melting of this bound state comes about as a result of high temperature and high density, the so-called Psi suppression. So what you're going to see in your detectors, instead of seeing two Psi's, you're going to see one because of this existence of the quark-gluon plasma. Is that clear? You melt a strong system. It's a phase transition. And it's been verified experimentally. In the year 2000, CERN showed that if this is the expectation based on the theoretical model, which is normalized with what is called the Drellian, the yields in these resonances, Psi, is meant to somehow drop slightly from the expectations that precluded the existence of the quark-gluon plasma. So at the moment, the jury is out. We don't have full proof that we have a quark-gluon plasma, but Jape size suppression is one of the signatures. So far, facilities that have been used to measure this are this one at AGS in New York at Brookhaven National Laboratory, the CERN SPS program. Just look at the energies. Okay, you can see here that the energy regime in the center of mass was the maximum of 4 GeV. It increased to about 17 GeV. The latest results that are coming out at the moment that are much debated come from a 200, almost an order of magnitude higher than the previous one. So you're now really beginning to put more energy into your system. You are really beginning to convince yourself that, okay, I might be seeing a quark-gluon plasma. What's going to happen in 2007 is that you're going to move almost 3 orders of magnitude. So now what we are building at the moment at CERN is a detector that I think will give us foolproof smoking gun that we will see another phase of matter. Whether it's a quark-gluon plasma or not is another point of debate. But what I need you to come up with now is an understanding that you have moved from 200 to 5.5 tera electron volt. So you're adding 1,000 times more energy into the system. So you better see something exciting. Okay, that's brute force physics. Okay, how do our colliders look like? Just to give you an impression, this is one example of a collider accelerator with 4 detectors, 4 Bose, Phoenix, Star, and Brahms. Of course, these detectors are very specialized. Okay, they measure different aspects of quark-gluon plasma because this quark-gluon plasma has got many signatures. Here is a simple example of what are called multiplicities. If you fire a proton, that was done at CERN in the late 70s until the early 80s. You fire protons on each other, a proton and antiproton, that's what you see. The amount of charged multiplicity that flies and gushes into the detector, these hadrons. So for orders of energy, square root of S, of about 200, 246, you see tens of particles. Okay? Now, if you scale this energy up a little bit to orders of 200 GeV with heavier nuclei, gold on gold, so instead of having one single proton, you've got Z number of single protons, so the energy scales likewise. Check what happens. And I'm looking for a single track here, back-to-back track. I missed this contamination. Yes, you look surprised. That's what you do. Here it was easy to, you can do some analysis. It wasn't easy, it was very hard, but you can do some analysis, Particle in the magnetic field will bend, you can do some calculations and work out what the momentum is, right? Now, when you're here, and you've been told to look for a track here, you can find it, because there is physics. Underneath this lies physics. You see, now you have to unpack an event underneath the contamination of thousands of particles. This presents a technical challenge. That's the fun part of experimental physics, is to find a signal in here. And people have done that very successfully. Now let's go back to the future. I have shown you that you've got 2 aspects of the strong force, perturbative and unperturbative. We know that the quark-gluon plasma, known as the QGP, is a new state of matter. It melts your Jape side, as an example. It will also give us an insight, because you're really in this range of, especially at Alice. Alice will be in the hard range. You will understand another insight. You'll develop new insights of how this very exciting but very difficult theory of strong interaction works. Also, at Alice, we will be able to create large volumes. So you'll be able to more or less see it. It will last a much longer lifetime than you've seen before. We will have large enough energy density that will sustain or incubate this QGP. So the most exciting challenge facing us now is to work on this LHC with 5.5 tera electron volt of energy. Let me tell you something about it. It's currently being constructed at CERN, the European Center for Nuclear Research. Have you all heard of CERN? Okay, it's a 27-kilometer radius ring, which is 100 meters below the sea level, straddles the Swiss-French border. So if you fire lead ions with a center of mass energy of 1150 tera-electron volts, this corresponds to 0.18 millijoule. Let's estimate orders of magnitude here. The amount of energy you need is a calorie. Okay, 4.18 calories, right? Sorry, 1 calorie is 4.18 joules. Okay. Now take a proton, which is 10 to the power minus, and you are a meter. You are of the orders of meters. A proton is of the orders of what? It's orders of 10 to the power minus 15 meters. So give this much energy. It's like giving you energy of 10 to the power 10 joules. You can do some algebra and do a comparative analysis. So you're giving these things so much energy more than they need. Enough to fire the whole universe, more or less. So, which is why we need to look at the interaction points where these particles collide. As I said, we have high energy density. We have a chance of seeing this quark-gluon plasma. Now I'll briefly give you an outline of this detector. This is the ALICE experiment. It's an experiment dedicated to finding the quark-gluon plasma in 2007. The group at UCT, involving Bruce, myself, and Spencer, and others, are involved with the design of one of the detectors here, which I'll talk about just now. ALICE stands for a Large Ion Collider Experiment. Okay, it's a collaboration of almost 1,000 members. Okay, the number has increased now to 1,000, coming from 28 countries and affiliated to 77 institutes. We have an army of physicists, informatics people, engineers, and South Africa is a member. Okay, how do you create collisions? You need beams. Lead-208 and lead-208. For comparison, we need PP, which is the simplest system to use. We need beams with high intensity. Thirdly, we end up accumulating a lot of particles. The rate of particles coming is very large. Most importantly, we end up with a huge amount of particles. Let's see the numbers just now. Okay, first let me show you some parts of the detector. In order for you to look at the center of where the collision takes place, we use the so-called inner tracking system. It's just a vertex detector. It tells you where the collision takes place. It's about a meter in diameter. It covers a certain region, which is central. To identify your particle and look at its trace as it moves away from the vertex, because when particles collide, particles gush out. So you need to track them. You know, it's like a scene of a crime. Sherlock Holmes finds the broken glasses. He needs to pick them up and collect and make out a reconstruction of where the original event took place. So we need trackers. They track particles as they move along this ionized gas. We need particles that visualize tracks in this region, which is where the UCT group is trying to understand. Because in order for us to work out this quark-gluon plasma, the JPSI, which I've mentioned, we need to understand the tracks. Because a JPSI will decay into a pair of muons and antimuons. Okay? So, by looking at the locus of the trajectory using these chambers here, one can just by carefully analyzing the path of the charge track, comparing that to the kinematics, you can just by applying relativistic kinematics work out the mass. Okay? So this tracker's main role is to reconstruct the mass of the JPSI particle, which decays into a mu plus mu minus pair. So this is an example of the event shape what you call the event topology of a shape side decay. Okay, and this is our main focus of one of the signatures. As you can see, a good reconstruction of the shape psi will give us this peak. Shape psi and shape psi prime. Here we have another resonance. You can see invariant mass. Mu mu plus. You can work out the invariant mass as the 4 momentum invariant mass. And then the shape psi lies here at 3.1 GeV. This here is what is called background. Okay? Because you've got like these thousands of particles. So you've got to search for this single track lying amidst a contamination of huge backgrounds. Alice uses almost all known methods. Okay? Alice will cover everything, from tracks to energy and everything. So we are sure that in the range of almost close to 100 GeV in transverse momentum, we should be able to calculate all these various signatures of the quark-gluon plasma, which I won't go into detail, but the most important of which is the decay of the shape psi, which is covered in this kinematic range of the muon spectrometer. Look at that. Someone asked me, tell me what this event is. We need to look at a track. Yeah. Can you work out any tracks here? No. Isn't it? So that's what's going to happen at Alice. If you fire lead on lead at 5.5 GeV. What will happen is that if you fire 200 nuclei per second, if the rate of particles coming out is 200 per second, you will store more than 60 gigabytes. Okay? Let's look at this. If you have 60 gigabytes per second, just do some simple arithmetics. You realize you have a huge amount of data for mass storage. Multiply this by that, what you get? A huge number, right? So you cannot even start to disentangle this picture. It's like taking your camera and exposing it to the sun. You're not going to see anything, right? So all you need to do is just put filters. So our current effort is to put a filter to reject background and select what? Good events. That's what in engineering is called pattern recognition. We need a very fast network to ship this data through. Finally, we need the grid. Have you heard of the grid before? The grid is a new philosophy of shipping data to areas that are far-flung. Let me explain to you the grid in a second. These are our 4 detectors. If they run at this very high rate, you end up with this amount of data, 5.8 petabytes per year. That is equivalent to 40,000 CDs per day. And then I'm told to find, maybe shape psi lies in CD number 1, and number say 3,400. Okay, and in order for you to do that, you require a lot of computers, of the order of 7 million spec 95. So P1. Okay, if you take Moore's law into account, of course, the numbers will decrease every 4 years. So you can't. I mean, this is almost a lost cause. However, as physicists, we try to find techniques to solve this problem. We need a grid. Since we have these huge data volumes, and we have a huge user base, and we've got a process of comparing real and simulated data, what we do is we take this data, compare it to the simulation, store it in data acquisition system, and analyze it before storing it on this grid. Now, what is the grid? The grid works as follows. Now we have 4 petabytes of data. CERN can't handle that. What CERN will do is that there will be the first repository of data. It's called tier 0. Okay? All this data that has been acquired will stay at CERN 2 petabytes. 2 petabytes, I mean, that's a lot. Even for CERN's 4,000 staff members, they can't handle it. And that's only coming from one experiment. It is the largest database in history. What CERN will do is they will fan this data to regional centers, okay, which are called tier 1s, somehow like a tree. Okay? These regional centers have got thousands of computers that will handle this data. Here's an example in France, the IN2P3. So it will be something of the size of the CESA in Pretoria. Then once they've done that, they'll filter this data and send it to another level, the tier 2. So probably if UCT is at CERN, they will receive data as a tier 2. Then the third person is you in front of the computer, sitting here at UCT or in Johannesburg or wherever, looking for an event, going through this tree here. Okay, so you'll be sitting online doing an analysis of data that's coming out at CERN in real time. I mean, real time, but it's real time. Okay, so this is what will happen come the 0 hour, 2007. Right, let me wrap up quickly. So we've got all these centers here, and one center will be Cape Town. Okay, I was showing you that this is much easier than this PP1. You can see that we have simulation of a PP collision where the jets are easier to pick up, whilst here the jets are clouded by background. Now, in the last 5 minutes, I'll talk about this filter. You remember I said that we have a technical challenge. We have somehow been able to take this data and ship it to all these centers. But this data is still like this. You have this cloud, you've got this blanked out screen. You need to do the physics. Your camera is exposed to the sun, so you need to put in filters. So this is what happens. All these detectors here, the time projection chamber, TRD, and so on and so forth, will receive data of huge volumes, 15 terabytes per second. They will be front-end electronics. You connect your hardware, your electronics. What will they do? They will cut out all the unwanted rubbish and scale it down to 25 bytes per second. 25 bytes per second multiplied by a month, which is what? How many seconds is a month? 1,000, right? 1 million. So you've got 1 million seconds, still comes down to what? Terabyte. It's a lot. Okay? And no computer can handle that. So we were asked to come into this level of filtering before we do any physics now, which is the high-level trigger. That is just a level of filtering data from background in order to select the real physics that can be stored into and be fed into centers for analysis. After analysis, then the theorists will look at the data. So this is all the hard work that experimentalists do to unpack this maze to unpack good physics amidst this maze of rubbish. Here's an example of the spectrometer. Okay? We are looking for this mu pair, mu bar, mu plus, mu minus. So we just write an algorithm, a computer code, that will select good events and reject events with low momentum, which are meant to be bad. So what this trigger does is it preserves a signal. So by imposing a certain cut, you cut on bad events, like so. What's that? Here's my particle. A good event will just come out like that with its partner, whilst a bad event will be uncorrelated. It can just come out like this. Okay? So that is bad data. That's all that rubbish. So we improve that rubbish by just first imposing a cut. Okay? By imposing a cut, you throw away bad events and retrieve as many good events as you can. So what this does is it improves the signal retrieval because you don't want to throw away the results, good physics, but you also want to throw away bad events. So for various cuts that you impose, we get the following rejection factors. So the more you reject, the better, but you can't even reject a good event. So you have to somehow play a very careful game of throwing away bad events without losing good results. What our colleagues at UCT have done so far is to show that by applying this algorithm that was written by a student here, Arthur, they showed that you can lower, this is background, this is rubbish. So you can lower, by if you impose this cut that I mentioned of 1 GeV, you can throw away a lot of bad events and also reject events that are not that are fake. Okay? So to start off with, what one can say is that already we are in production. We are beginning to play around with cutting away bad events. Of course, the hardest part is to look for the good signals, which can be obtained by playing around with some pattern recognition tools. What you've done so far is to set up a tier 2 center. Okay? Bruce is the man in charge of this cluster. It's got 20 nodes. We're running these 20 machines with the following specs. Okay? So we're starting out small to see whether we are in a position to be able to enter into this new domain of physics. When Alice is complete, we will be in a very strong position to study the QGP after RIG, which has been in the headlines of late. Secondly, because of the fact that we are firing these particles at very high energies, we are faced with immense technical challenges. Okay? We've got to build good detectors. You need to write code, which is both online. So sitting there, you need to get fast online intelligence that will select good or bad events and throw away bad ones. Someone will be doing computing at home, doing the analysis that will be compared with theory. So you require a farm of computers. You'll need to buy a lot of tape for mass storage, and a new technology will be spawned, the technology of grid computing. Just like the World Wide Web was started at CERN, grid computing promises to be another level of development of high-tech computing. So basically, physicists are now faced with the problem of looking for the QGP. It's a simple physics problem, but they are faced with immense technical challenges. In order to surmount those challenges, they invent new things, and they will spawn new technology. And I'm proud to say that UCT will be one of the active research groups that will be active in understanding nature, and yet at the same time meeting the challenges by inventing new technologies, which is what physics is all about. You meet challenges, you reinvent yourself, and live up to the challenge. Okay, I'll not say much about this, except I think I'm done now. Yeah, I'm done. Thank you.
Questions, comments?
Can you go again on how you do the rejection of bad data? Will that be on what you simulated already that you have and then feeding on different points and then doing a comparison and chopping off the wrong data?
Okay. You remember I showed you a hierarchy of data filtering. First, you have like hardware, electronics, right? You cut off the zeros. Second, you have an intelligence of processors. Okay, that are hardware, you can program them like an engineer. You know, engineers run code which is called, they do FPGA programming, right? This is a third level of filtering where you use computers. Okay, the high-level trigger. So a rough cut gives you this. Sorry, that's a level higher than, that's a more rough level. So look what happens. If you have a rough cut, you do get rid of bad events, right? However, just because you've imposed such, it's like bringing a cannon into a gunfight, okay? You'll take out your enemy, but there'll be a lot of damage, won't it? So, now you require a more sophisticated technique. So that's what we do. So you have imposed the cut, but this cut is now sharp. It's sharp such that you don't even, because here there's a lot of physics here. I'm sure you can see it, but you'll see it in the future. There's, underneath here lies a lot of physics. So with this higher cut, which is brutal, you lose physics, which is not what you want. Because after running for a year, you'll only get 15,000. We'll get 500 or so out of 32,000 particles. So you cannot afford to lose these good signals. These signals tell you whether you have a QGP or not. Although you want to get rid of the background, but you're going to do that with such finesse and art that you don't lose good signals. Okay, so the high level of triggering is a smoother, a more refined scalpel to select, to reject backgrounds. Okay, does that answer you?
Obviously, all the data at the moment is simulated because we don't have a collider at the moment. So we simulate physics that we understand perfectly, and then we apply the filter to it and we see what comes out. And we compare those two things, what we put in, which we know because we simulated, and what came out. And so, yes, we know the kinematics of every particle that we simulate, and we know the kinematics of every particle that comes out. And that's how we develop that trigger.
I said, okay, no, this is not real. Okay, I understand the question. This is Monte Carlo. Okay, this experiment is currently being built. What you do in physics is before you start an experiment, you write this Monte Carlo code that will replicate your detector. Okay, so this is not an experiment online. It's not a hot experiment. We're running this Monte Carlo code. Yes?
Trying to envision what will happen when the collider starts to work. At the top level, have a zero tier, have a one tier, you have a second tier.
Right.
Then the top tier that you have the users.
Yes, tier 3.
Yeah. Now, I think the signals will be going through different institutions. How will it be coordinated? If maybe the data center, so in case you're just looking for one tiny signal, how will you coordinate all these institutions? So in case you get a signal, how are you going to be sure that you got the right signal? You spot the right signal you're looking for, that signature. How do you be sure? Because there's so many institutions that are working real time.
Mm-hmm.
But how are you sure? Well, maybe before I ask that question, this software is going to be developed. It's going to be put in a SAN database. Is that right?
That's right, yeah.
Okay.
It's been developed.
All users will have it.
That's right, yeah.
You're doing just this programming, this. Is anybody or any institution also on this program?
That's right, yes. There's an institution in India. Okay. The spectrometer, okay, this arm. There are two groups that are involved in looking at that are involved in writing the filter to look for this JIP size, right? One is based in Kolkata and us at UCT. Okay? So, when particles collide, you have all this data coming out. So you apply the filter. The filter tells you whether you have a good or bad event. That takes place at CERN. Okay? So you look for results that are validated by the high-level trigger, because all you do with the trigger is you bias your results to gauge in the region that you look at. I mean, you can't just look for something without looking at the range. So the trigger just gives you a ballpark where you can start looking for results. Okay? So you look for, say, I'm looking for data which has been validated by this filter. Then you know where that will be. Okay? So you've got all these centers with particular areas of expertise.
Yeah, this isn't like SETI where they're looking for like one signal in a batch of data. The data is mirrored. Okay?
The same data transmitted every time.
Not exactly the same, but the database will know where it is. You write a little script that says, I want to find something. You send it off to Elliot, which is our group, and Elliot will say, okay, this script needs to run over there. And run over there, where the data is that you're actually interested in, and send the results back. So you don't actually have to know where the data is. You don't have to know where the signal was found. Nobody has to know that. Only the very first level of processing, data will mark the data and say, okay, this is a certain kind of event, that's a certain kind of event. So your little script that needs to make submit it to the grid that cares and use it.
You just do something massive.
Right. And every subpart has the interface with that so that we go in. Yeah, there's an offline manager and there's a grid manager. And you can put those together as well as the data.
Okay, these are the how the tiers work. I mean, the tiers just stand out, and these guys can talk this one, you know.
Another question? I'm sorry to ask this
Sure.
question. But are we not changing the face of creation by doing this?
Nature Mem created this 15 billion years ago. We are looking at nature. We're not changing anything at all.
We are. We're using mash things together to create massive amounts of data, massive amounts of energy.
John, I need your help, please. It's a philosophical question.
I think that what Zeblon and friends are doing is just recreating the conditions that occurred, we believe, very early in the history of the universe, but on a much smaller scale, and also in some way replicating conditions which are a little bit like what might be going on inside some neutron stars. So they're just exploring the laws of nature which have been there since the beginning, and just, as I said, recreating situations which we believe have occurred or are occurring elsewhere in the universe.
I can't help feeling vaguely discomforted about having these tremendous amounts of artificial energy pumped into my universe, and if somebody else came to do it from another universe, then we'd say stop.
In fact, collisions like this do take place in the universe today, because cosmic rays contain very, very energetic particles. They're very energetic nuclei, and so collisions like the sorts of things that Zeblon is planning to recreate do occur out in the universe, but they happen in uncontrolled ways, and in ways that we cannot observe directly, because this sort of collision that takes place in the universe naturally is very few and far apart, and we don't know when they're going to happen, but they do occur. So what in this colliding you try to do is to make it happen in a way.
A question that I don't know you might think is sort of out of the blue or something like that, but it actually is a serious question that serious people have thought about, particularly in the issue of trying to create a quark gluon plasma. People did actually begin to wonder, actually, have we thought about this? Are we sure that we're not doing something that we should, if we don't understand this thing that we're trying to create, maybe it can spin out of control or something like that? And so it's a natural concern, and so actually it's not an unreasonable question. I'm happy to say that actually it was studied very carefully, and the conclusions that John just relayed to you are indeed in line with the conclusions of the panel. It was a very eminent panel, maybe it's a panel of very eminent people, I'm not sure. But very eminent people sat about and thought about this a long time, particularly for these types of experiments, and indeed thought about it long and hard, because it's a serious question that everyone is entitled to ask. So I just thought I'd say that.
I'm just going to say that if you're interested in pursuing it further, I could give you references for the studies that were done, so you could have a look at them and see whether you're convinced by them.
Yeah. Other questions? Yes. Excuse me? The question, forgive me for paraphrasing, and correct me if I got it wrong, is, are we sure we should be doing this sort of thing, basically? We're trying to recreate in an experiment conditions that we believe may have existed at some point in the universe's existence, and should we be careful about doing that? Of course not. And so it might be an issue that seems silly, but it's not an unreasonable thing to ask.
Yeah.
After all, we're doing exploratory science here. If we exactly knew what we were doing, then there'd be no point doing it. So it's a reasonable question to ask. But as far as we understand the science that we already know, the answer seems to be that we're safe. And the point being that we know, just by observation, that there are events occurring all the time, just beyond our atmosphere, for example, and into our atmosphere, cosmic rays enter with extraordinary high energy densities. and our atmosphere isn't being ripped apart or anything by those, and so we're probably not doing anything more harmful than what those are doing. But it's a question worth considering. Any other questions? Okay, so let's stop here.